Hello, in this video we are going to go over substitution versus elimination and how that can affect different things like entropy, temperature, Gibbs free energy, etc. So in the last video we saw that there is an E2 elimination reaction, so that's a second order elimination reaction. And we also saw that there is an E1 reaction, or a first order elimination reaction. So now let's see what the entropy is for a substitution reaction versus an elimination reaction. Does entropy increase or does it decrease? So let's write out some examples here. So I'm going to start with elimination reactions. So we saw that for an E2 reaction, we have our substrate with the leaving group and then our base. And we know that the base is going to take a hydrogen from one of the beta carbons. And then the shared electrons will be left as a pi bond, which will cause the leaving group to leave. So we end up with an alkene, our conjugate acid, and our leaving group. And then for E1, we saw that the leaving group leaves first. And we form a carbocation intermediate. And the base is going to then take a proton from one of the beta carbons. And then we form a pi bond. So we end up with an alkene again, our conjugate acid, and the leaving group. Now let's refresh our memories on SN1 and SN2. So for an SN2 reaction, we have an unstable nucleophile that is going to attack the carbon next to the leaving group, and the leaving group leaves. So we end up with our new product with the nucleophile attached, as well as our leaving group. And then for an SN1 reaction, we have a weak nucleophile because the leaving group leaves first. So the nucleophile doesn't really matter. And then we form a carbocation intermediate. And the nucleophile will then attach to the positively charged carbon. And we end up with our two products. Okay, so looking at all four of these reactions, you might have noticed that in an elimination reaction, we have 3 moles of products. So regardless of E2 or E1, we always have 3 moles of products. But looking at the substitution reactions, we only have 2 moles of products. So elimination reactions start with 2 moles of reactants, but end up forming 3 moles of products. So there's more disorder, which equals a positive delta S. So entropy is increasing for elimination reactions. But for substitution reactions, the entropy isn't really changing that much because we're going from 2 moles of reactants to 2 moles of products. So there really isn't a change in entropy in that sense. And of course, we could go into more detail and figure out if there's more freedom of motion, etc. But for now, let's just focus on the moles of reactants and products. Okay, so how does temperature affect substitution versus elimination reactions? All right, so let's refresh our memories on Gibbs free energy, which tells us that delta G is equal to the change in enthalpy minus the temperature times the change in entropy. Now remember, for elimination reactions, we just said that delta S is positive because we're forming more moles of the product. So that means negative T delta S will be negative. Now let's ignore delta H for now. We know that for spontaneous reactions, delta G is negative. So for elimination reactions, that tells us that the temperature should be high. In order to maintain a negative delta G value. So if the temperature is really high, then negative T delta S will stay negative, right? Which will keep delta G negative. So elimination reactions favor higher temperatures. Now, substitution reactions, on the other hand, they aren't affected by temperature as much. So we'll just write substitution reactions Oh, my pen is stopped working. There we go. Substitution reactions aren't affected by temperature as much. And again, on the last slide, we said that the entropy of a substitution reaction isn't changing that much since the amount of moles stays the same for the reactants and the products. So that kind of makes sense that substitution reactions, they don't care as much about temperature, or they're not as affected by temperature. Now, the other thing, remember, looking at the last slide, elimination reactions use bases because bases take protons. But substitution reactions use nucleophiles because nucleophiles will attack and bond. So let's talk a little bit more about nucleophilicity versus basicity. So what makes a good nucleophile? Well, remember we said that for SN2 reactions at least, we need the nucleophile to be unstable, which just means very reactive. And another thing that we want to take into account is how big the nucleophile is. If you have a really large nucleophile, it's going to have a hard time attacking your substrate. So we want a nucleophile that's smaller. So it shouldn't be bulky. So we'll say not bulky. Now, you'll also recall our handout on nucleophiles and bases. And nucleophiles have to do more so with the rate of a reaction, or kinetics. So if we're considering how quickly a reaction occurs, we want the barrier, the activation energy, to be smaller in order for the reaction to occur quickly. So we want the activation energy to be small. So good nucleophiles have small activation energies. Okay, so then let's ask what makes a good base. Well, again, we do want them to be reactive, so they should also be unstable. But the size of a base doesn't really matter because they're just taking a proton. And protons are really small and easily accessible because they're always on the outside, right? Or at least for our purposes, we can say they're kind of pointing out. And so the base can very easily take that hydrogen. So size does not matter for the base because we are taking a proton, which is easily accessible. Oops, I spelled which wrong. So remember, for bases, we care more about the stability of the product or the thermodynamics, right? So remember, up above with nucleophiles, we care about kinetics, or the rate of the reaction. But with bases, we care about the thermodynamics. Thermodynamics. So we want the difference between the reactants and the products to be quite large. So we want delta G to be very large and negative so that it's spontaneous. Okay. So now let's talk about nucleophilicity in a little bit more detail. So we're going to kind of think about the activation energy, or kinetics. All right, so let's compare three different nucleophiles. Let's compare OH minus, and then let's say we have an oxygen connected to a tert-butyl group. And finally, let's say we have an oxygen connected to a methyl group. So which one of these nucleophiles would be the best nucleophile? And remember, we just said that the size of the nucleophile matters. And so this is what we call the sterics, or sterics of the nucleophile. So really what we're saying is how bulky is the nucleophile. So which one of these nucleophiles, if we're thinking about sterics, is the best nucleophile? The first one, right, on the left, the hydroxide ion, that is the least bulky out of the three. So that would be the best nucleophile. Now, comparing the other two nucleophiles, which one is the worst nucleophile? The one in the middle, because that is the most bulky nucleophile. And then the one on the right is intermediate. So it's not as good as the hydroxide ion, but it's not as bad as the bulkiest nucleophile. Now also remember that solvation can affect how well your nucleophile attacks. So remember that if we draw the periodic table or part of the periodic table, and let's say we're comparing nucleophiles in a row. So let's say these are all negatively charged. Remember that if something is less electronegative, it's more likely to give up its electrons or share its electrons with something else. Because if something is very electronegative, it's going to hold on to those electrons really tightly. So nucleophilicity will increase going from right to left. And that actually doesn't, that's not affected by the solvent necessarily, but what does affect the nucleophilicity is if we're going down a column. So if we say that we have all negative ions going down this column, and let's say that we are in an aprotic solvent. Or a polar aprotic solvent. Which of those halides would be the most nucleophilic in an aprotic solvent? The fluoride ion. Now, what if we're in a polar protic solvent? So remember, in a polar protic solvent, we can have hydrogen bonding. So now which halide is the most nucleophilic? Iodide. So remember, fluoride ions, or even fluorine atoms, can hydrogen bond. So if you have a polar protic solvent, that's going to solvate the fluorine atoms or the fluoride ions so that they can't react. So iodide, which has a more spread out negative charge since it's so large, it won't be as tightly solvated and it can't hydrogen bond. So that's going to be our biggest or best nucleophile in a polar protic solvent. So these are all things to think about when we're considering, what makes the best nucleophile. We have to think about the size as well as what type of solvent we're in. Are we comparing nucleophiles in the same row or in the same column? And this is a lot to remember, so I do recommend making flashcards or, maybe just going back through these slides occasionally just to refresh your memory. So now let's look at factors that affect basicity, which is really just the Gibbs free energy, because remember on this slide we said that we care more about thermodynamics for bases. So how large and negative is our Gibbs free energy? So let's talk about that. So again, remember we want an unstable base. So that means that it will have a negative charge. There won't be any resonance, so no resonance, because remember, resonance stabilizes a base. And we also want a small electronegativity value, because if something has a large electronegativity value, it wants to keep its electrons. So we want a small electronegativity value so that it wants to give up its electrons and take a proton. Now we also want a base that has a stable or weak conjugate acid. Because remember, strong acids produce weak conjugate bases. So if you have a strong base, that will have a weak conjugate acid, and we want a strong base. We want an unstable base. Now, sterics or size doesn't matter as much for bases, so we don't have to worry about that too much. So since a base is just taking a proton, and remember protons are pretty easily accessible, the size of the base doesn't really matter. Okay, so I think we'll stop there for this lecture. So really we went over different factors that can affect elimination versus substitution. So if we go back to the first slide here, we said that elimination reactions have more entropy, so their disorder increases, whereas substitution, we don't really see an increase in entropy. So when we think about temperature, because there's an increase in entropy for elimination reactions, that means that we want a really large temperature so that delta G will definitely be negative. But additionally, we talked about bases and how elimination reactions use bases, and we want the thermodynamics to really take control for elimination reactions since we're using a base. So delta G has to be very negative. Now for substitution reactions, it doesn't matter as much, but when we start talking about nucleophiles versus bases, remember we use nucleophiles in substitution reactions, so we care more about the kinetics. But we use bases for elimination reactions, so we care more about the thermodynamics. Now in both cases we want something that is unstable, so very reactive, but we said that for nucleophiles the size matters. It can't be bulky. For bases, however, the size doesn't really matter since it's just taking a proton. And then we just summarize nucleophiles versus bases. So these are all things to think about with these reactions as we go forward. So in the next lecture, we'll talk about bases that are not nucleophiles. And we'll kind of talk about, well, what if I need a base that won't attack, so it won't act as a nucleophile? Or what if I need a nucleophile that won't act as a base? So we'll kind of step through that a little bit more. So I will see you then.